Hello, my name is Alex Matthes. I am a student at the College of Engineering at The Ohio State University. Today I'll be presenting my research titled 3D Printing and Sustainability. This project focuses on how 3D printing practices can become more sustainable, reducing reliance on non-renewable resources. My research question is, how can 3D printing facilitate sustainable practices and reduce human non-renewable resource usage? This question is important to environmental science because 3D printing is increasingly replacing traditional mass manufacturing, yet conventional plastic filaments still contribute to microplastic pollution and waste streams. Finding sustainable alternatives is crucial for reducing environmental harm while maintaining the benefits of distributed manufacturing. Researchers around the world are actively working on sustainable 3D printing. For example, various researchers have explored developing recycled and bio-based 3D printing filaments using agricultural waste materials. Researchers have also experimented with biodegradable filaments for zero-waste fashion design. Common equipment includes extrusion-based 3D printers such as the MakerBot replicator that I have pictured in the poster. Also, machines to measure material tensile strength. Researchers often test new filament materials by measuring various factors such as elasticity, biodegradability, recyclability, and tensile strength. In the research explored in my poster, various materials were tested, including plant-based polymers and recycled plastics. Samples were printed and subjected to tensile strength testing. Tensile strength tests involved applying a slow, steady load to printed objects until they broke. This helped assess whether sustainable materials could match the mechanical performance of conventional plastics. On my poster, Figure 1 shows the MakerBot Replicator 5th generation, a common household 3D printer. Figure 2 is a bar chart summarizing the tensile strength data for various filament types. Materials tested include PLA, ABS, PETG, nylon, and polycarbonate. Figure 3 displays an example spool of green filament, one that you would commonly see used on a conventional 3D printer. Key findings from the tensile strength test show that polycarbonate had the highest strength at approximately 70 megapascals, while PLA, a biodegradable material, had moderate strength at around 45 megapascals. Overall, the results suggest that while petroleum-based plastics such as polycarbonate are stronger, plant-based and recycled materials like PLA still offer sufficient strength for most everyday applications. This is significant because it indicates that switching to sustainable filaments does not require major sacrifices in part performance, an encouraging finding for future low-waste manufacturing models. This research shows that 3D printing can become more sustainable by transitioning towards bio-based and recycled materials. Current research is advancing in this area, exploring additives to improve the strength of bioplastics, as well as closed-loop recycling systems for used filament. Future research focusing on improving the mechanical properties of sustainable filaments and developing standards for filament recycling programs is exciting. Potential real-world solutions include creating decentralized filament recycling hubs, encouraging manufacturers to design products intended for easy at-home repair and eventual recycling, as well as increasing investment in biodegradable composite materials. In conclusion, sustainable 3D printing offers a promising path forward in reducing plastic waste and conserving non-renewable resources, as well as decentralizing manufacturing, reducing the need for large mass manufacturing facilities. Through smart material choices and innovation, 3D printing can significantly reduce the environmental footprint of our modern manufacturing. Thank you for watching my presentation.